So order's going to be one of those, and it doesn't really matter which one goes first. It's just one spin, then the other spin.
Yeah.
2. Then we can start filling the 2p orbitals. Again, we fill each one partially before we start to fill it completely.
Okay.
And then once this one's filled, we move to the next level. So that's me 3s. Once we fill that full orbital, we move to the next 3p orbital. We partially fill it. When we finish, then we switch up to this one. Once that's filled, the next one is actually going to be the 3d orbital after 4s.
So you wouldn't go to 4p?
Nope. So that's where the order kind of gets, just due to the energy level.
Yeah.
And this is where there's a lot of confusing stuff, but you just have to memorize that. After you finish filling the 3p and then the 4s, you go back a step and fill the 3d. And that's where that kind of diagonal diagram is really nice. It's because it goes like this. Because you go the 3p, then 4s, then the next one's going to be the 3d. Again, 1, 2, 3, 4, 5. Then you can fill the next 1, 2, 3, 4, 5. Once that one's filled, you go back to the 4p. So 1, 2, 3, then 4, 5, 6 for that one. Once that one's filled, then you can start the next one, which will be the 5s. Then, since this one's filled, the next energy level is going to be the 4d. Then 5p. Then 6s.
Okay.
So, as long as you can kind of remember this diagonal pattern,
Yeah.
it's pretty straightforward.
Gotcha. Okay.
Then just remember there's some exceptions where it might go, I'll have to figure out which ones. Razor doesn't work. Where some of them, instead of filling each one partially, it'll fill this one and then this one partially. And then instead of adding an electron here, it's going to add an electron back in one of these just because it's going to be a lower energy. And it's a very odd situation, and it's very specific to certain elements. So those are going to be ones where you'd have to go and memorize and see why. And again, it's just due to the fact that each orbital with different shapes will want to be filled first. And in a certain case, let's say, I want to say it's beryllium, but in certain cases, it's going to fill each one partially, and it's actually more stable to have the electron finish filling one of the suborbitals rather than going to one of the other empty orbitals.
Gotcha. Okay.
So, and again, that's only for an exception. Just remembering this order for filling is going to make it a lot easier.
Okay. All right.
So, I don't need to save that. Going back to this, so that's your basic electron shell concept. Next, we're going to go VSEPR. So, SP, so pair. I'm sure that's definitely spelled right. But valence electron shell pair repulsion. So let's go with, let's say sulfur. Again, it's going to want to have 8 electrons in its outermost shell.
Okay.
So sulfur currently in a stable state has, let's see, 3, 4, 5. It has 6 valence electrons. That's just going to be all the electrons in its outermost shell.
Okay.
So sulfur's going to be 1, 2, 3, 4, 5, 6. It'll probably end up being like this, just so those are separated. So in order for this to have the full 8, it's going to need 2 electrons.
So big, plus 2.
It needs plus 2 electrons. So for it to get the 2 electrons, this is going to be the easiest way to look at it. Let's see, carbon is 4, carbon, nitrogen, oxygen, fluorine. So valence, it's got 4, stable needs 4 more. Nitrogen, and it's going to be 5. In order to make the 8, it needs 3. Oh, it has 6 valence electrons, needs 2. This is going to be the number of bonds that each of these elements want. So let's say, so let's say we have 2 hydrogens, 2 carbons, and 2 more hydrogens. So this one, the carbon has 1, 2, 3, 4 valence electrons. 1, 2, 3, 4. Hydrogen has 1 each. And this is where, when we draw the line, just think of each end of the line as one of the electrons.
Okay.
But now that this is here, so this carbon now has 1, 2, 3, 4, and 5. Then I draw this one, now has 6. Then I draw this bond, this carbon has 7. Let's combine this. So this carbon has 1, 2, 3, 4, 5, 6, and I'm just going to keep this electron, that's 7. So obviously hydrogen, again, being hydrogen only has the one s orbital. So it just wants to fill it all the way, so it only wants 2. So hydrogens are good. Carbons, not so much, because they have 1, 2, 3, 4, 5, 6, and 7, and then it's symmetric, so the other carbon also is not there. Easy. The most stable way to fix this is just to bond these 2 again. So now it's 1, 2, 3, 4 bonds on this carbon, and 1, 2, 3, 4 bonds on this carbon.
Okay.
So let's say nitrogen has 1, 2, 3, 4, 5. I'll do this. Keep the electrons separated. So it needs 3 to make an octet. So just looking at using just hydrogens just to stabilize it, we're going to have this 1 pair, and so that's 1, 2, there's a hydrogen, there's 1, 2, there's another hydrogen, so 1, 2, 3, 4, 5, 6, 7, 8. 1 bond, 2 bond, 3 bonds. So the number of electrons that it needs is the number of bonds that it wants to have.
Okay.
The other way that they represent that is to say the number of valence electrons and minus lone pairs minus the number of bonds should equal 0. So for this case, it's 5 valence electrons, and we have 1 lone pair, or sorry, the number of unpaired electrons. So there's 2 electrons. We have 1, 2, minus 3 bonds. And that equals 0 because we have 1, 2, 3 bonds, then our 1, 2 lone electrons, or unpaired electrons. Let's try oxygen now. So oxygen has 1, 2, 3, 4, 5, and 6. So for this to be stable, and this is where learning about the electron geometry is going to be important, because it's not going to want to do this. Because we know that this is going to look like this. Because we're all familiar with H2O. So oxygen has 6 valence electrons. It wants 2. That's going to be the number of bonds. So this is where, let me go back to the assignment. This one. So looking at this nitrogen, again, nitrogen has naturally, let me see, I did that a second ago. Yeah, nitrogen has 5 valence electrons. So it's going to want 3 more electrons. So in this case, 1, 2, 3, 4, 5, 6, 7, and 8.
7 and 8. How do we count that?
This line, each end of the line is going to be an electron.
Okay, gotcha.
So that's 7 and 8. So this has an octet, but if we take the 5 valence electrons, I'm just going to, let me see if I can just copy that down actually. And see. So it looks something like this. 2, 5, 6, and 7, 8. So we have nitrogen has 5 valence electrons. 1, 2, 3, 4, 5, 6. 6 unpaired. Minus 1 bond equals -2. So that's what this method is for finding the formal charge. You want your formal charge to be 0.
Okay.
So in this case, this bonding method is going to be terrible. And that's where this -2 comes from.
Okay.
Is from looking at the formula for formal charge. Again, this oxygen having 6 electrons in its orbital, it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So it's got its octet, but we have 6 electrons in its valence, so -1, -2, -3, -4, -5. So we have one additional, we end up with a total of 1 additional because we have 1 more valence than the formula. So again, just actually writing that out. Oxygen, 1, 2, 3. Let me see. How did they write it out? 3, then 2 lone electrons. We have oxygen, 6 valence. We have 1 minus 2 unpaired, minus 1, 2, 3 bonds, equals plus 1 on the formal charge. So again, this not equal to 0, it doesn't like it. It's going to be a non-optimal structure. This one, obviously, it's not great because you still have the -1 charge, but it's about as close as you can get. Or, yeah, because this oxygen here isn't going to be at its best. But yeah, and this is where remembering electronegativity, because the oxygen is going to be more electronegative. It's going to tend more to take an electron than the nitrogen.
Okay.
And that's where the formal charge is more likely to have the -1 than the nitrogen.
Okay.
So using your formal charges and then your what's it called, electronegativity. And then electronegativity is going to be one where you'll have to look and memorize the organization. So B's start at 1, increase by 0.5. The next row starts at 0.9 and it increases by 0.3. So once you get to the end, this is going to have a lower electronegativity than the fluorine.
Okay.
That's, I think, as much as I can